Hi, welcome to Online Logic. Today we're going to be looking at 7.5, the conditional proof. Welcome back everyone. Let me start off today we're going to be looking at 7.5, the conditional proof. But I have to apologize because I've had a sort of technical failure in terms of the tablet computer I've been using. There was something that broke down on it. I've ordered a new part, but I'm waiting to get it back. So in the meantime, we're just going to do this old-fashioned with pen and paper. So hopefully you'll be able to see this okay. I'll try to write big as we go through. But let's start off with sort of a brief review, right? Last time we looked at we looked on the one hand at rules of replacement and rules of implication. Right? So the rules of replacement, these are essentially deal with logically equivalent pairs that we can swap in and out of our arguments so as to build the deductive proofs. And rules of implication are sort of argument sequences that require the full line. So we're gonna add two more things because we'll see that the rules of implication, the rules of replacement that we've covered in the first four sections of chapter 7 have really allowed us really a fabulous tool for building proofs. But it's still incomplete. In fact, not everything that could be proven deductively is proven if you only have rules of replacement and rules of implication. So we're going to see in 7.5, we're going to introduce a new thing. We're going to call this the conditional proof. And the conditional proof operates essentially by when you get stuck in a problem, the conditional proof allows you to begin to build a proof sequence. And I guess the best way for me to explain it is actually do a couple problems for you. So let's start off here and let me just show you a real simple problem. Let's imagine, for instance, you have this problem. If A, then B and C, line 2 here is going to be B or D, then E, right? And then the conclusion you're looking for here is if A, then E, okay? Now, if you took a look at this problem, and if you want, you can pause the video and sort of take your time and look at this, what you'll find is that none of the rules of implication or anything are going to help you here, right? Because you can see to get E, you need B. You could add D potentially, right? But in order to get B here, you need A. You don't have A. So what can you do? Well, you can do this thing called a conditional proof. And here's what you're going to do is the first line of conditional proof is always going to be written to the right. And what you're going to do is you're going to write line 3. You're going to add your assumption. You're going to put A here. Okay, we're going to assume A. And this is called our ACP, or the assumption for the conditional proof. Now, some important things about what happens when we make an assumption. Right, what we're going to do here is the conditional proof exists essentially by creating an assumption. And if you make that assumption, can you result in a conditional statement, right, that can then be used in the line of sequence. Now, let's sort of see. I think the best way for me is just to run through the problems. Remember, the assumption, we don't know if it's true or false, right? An assumption in itself, you can't just make a problem up, and your assumption can't just make the problem valid, right? But let me run through the sequence here. So I'm going to assume A, right? Now that I have A, right, line 4, right, since I have A, I can get B and C, right, because this unlocks this. I've got B and C, and so that would be, I'm still going to write it off to the side here, right? Whoops, I made a mistake there. I should have wrote it right here. B and C, right? And then I'm going to put lines 3 and 1, or 1 and 3 modus ponens, because that's the rules I used, right? And now that I have B and C, line 5 is I can just simplify to B, so that's line 4 simplification. And then line 6 is addition. I'm going to add this, so that's going to be B or D, right? And that's going to be line 5 addition. And now that I've added B or D, line 7, I can get E, right? And that's lines 6 and 2, modus ponens. Okay, now you see what I've done here is I've written all of the I've written my assumption here, and then if I make this assumption, here are the things I can deduce, right? Now that I've gotten this, you can see here it basically demonstrates that if I have A, then I can have E. That was actually the conclusion we were looking for, right? And so the conditional proof means that once I've written this off to the sides, I can now discharge my assumption. So the first step here is to make your assumption. The second step is to make your deductions using the rules of replacement and implication. And then line 3, you're going to discharge. You're going to discharge your assumption. And what the discharging your assumption means is it means that you're going to get rid of this line, which means line 8 here is going to be if I have A, then I have E. That's A, then E. And over here, what I've done is I've utilized what we would write conditional proof, lines 3 through 7. 3 through 7. And now that I've discharged, so what does this mean? Let me sort of get a pen here, maybe sort of draw things out. Now, you can see here that this was the conditional proof we used, CP, right? But what this means is that since this was an assumption, we don't know if that assumption is true, that none of these lines actually count as valid lines in the argument. But it does demonstrate that if you had A, you could get E using these rules. And so that means that once we've discharged our assumption, and then we write the new conditional statement. Once we've done that, that means that line 8 is a valid line. So that means the only lines that are valid in the argument here is line 1, line 2, and line 8, right? And of course, we know that line 8 is the conclusion. The important thing about doing the conditional proof here is once you discharge, right, once you discharge your assumption and write out your conditional statement here, which means that, remember, this is always going to end up being the antecedent, and this will always end up being the consequent of your conditional. Remember, this here is the antecedent, and this is the condition. This is the consequent, right? So that's how this is what the indirect proof is. But once you discharge it, you can't use any of your former lines ever again. Your assumption doesn't count, right? So that's something to remember. What you need to remember is, number one, is that proof lines don't count as valid lines. Okay? That these proof lines don't count as valid lines. And number two, once discharged, right, the proof sequence, whoops, I'm sorry, you can't see here. The proof sequence is no longer used. Okay, you probably can't see these because I realize I'm recording this on the video, right? But I want you to see how you've done this. This is why you always write your proof sequence off to the side with a line next to it. So that way it's clear that none of these things here are going to count in terms of the argument. But remember, you do that, you make your assumption. Your assumption is going to be the antecedent of a conditional statement that you'll discharge. You use this assumption to work out the problem, come up with a proof sequence of lines, and then eventually you come up with something in the end, and once you're done with this, you discharge it by placing the E into the consequent position of a final conditional. So let me do another problem. Hopefully this makes sense on what the conditional proof looks like. I know it's a little bit different in terms of, typically I like to do these problems with the computer here, so I'm sorry about that. But let me do another one here, because you're going to see here that you can actually do a lot of things with the conditional proof. You can, in fact, embed certain arguments. You can embed a conditional assumptions within conditional assumptions, or you can use multiple conditional proofs throughout an argument after they've been discharged successively. So let me see, put the 3, there's G or J, then H or K. Now, you can see here in this problem here, you can see always start by looking at the conclusion. I have H or K. Well, here's an H, here's a K. Obviously, if I get the H by itself, I'd be in good shape. I can't, right? You can see here, here's a G. Yeah, if I could get the G by itself, I could get H or H. I could simplify. I can add. I'm running into trouble here. What? Because obviously, you only want to use a conditional proof when you want a conditional statement to conclude with. So, how can we do this? Um, well, let's start off with this. It seems like I should. Let's imagine I just assume G. If I could get if G then H and then um, J then K, right? I might be able to build up a constructive dilemma, perhaps. So let's see if we can do that. Let's just run through it here. So line 4, and I'm going to use a proof sequence. I'm going to assume G. So this is my ACP, and again, that stands for the assumption for the conditional proof. Once I've assumed this, well, obviously I can get H and I, right? That's line 1 and 4, modus ponens, right? Once I've done that, I can simplify. So that's going to be line H, so that's going to be line 5, simplification. Now I'm going to discharge this, so I'm going to write the line off to the side here, and then now in line 7 here, I'm going to write if G, then H, right? Again, because my assumption here ends up being my antecedent, right? And this ends up being my consequent in the sequence, okay? So that means I've done this problem, so now I have to discharge it, which means line 4 through 6, conditional proof, okay? And I've discharged it, and I've written over the line. Now that I've used this, now what can I do next? Well, you can see, what if I assume J? I could get J then K as well. So let's do that. Let's do another assumption. Let's assume J, that's ACP, right? Line 9, if I can get J, I can unlock K and L, right? Since I can unlock K and L, that would be lines 8 and, 2. 8 and 2, modus ponens. 10 is going to be K, simplification. That's line 9, simplification. Right? Let's discharge it now. So that's going to be line 11 is going to be if J, then K, right? That's lines 8 through 9, conditional proof. Now remember, once it's been discharged, that means that all of these sequences are off the table. You're not allowed to use these. The only reason we keep them here is so that we can show that if you made that assumption, it would be a valid, that you could result in a conditional statement. Yeah, right. It means that if you assume J, you will result in a K, which means that if J, then K is a valid line within the argument, right? Because think about it. If J, then K, you're still saying if this is the case, right? You haven't said that it is the case, right? But so you create a conditional statement that's valid. But all of these deductive lines, these are no longer count. These are out of the proof, right? We're just keeping them there. So then now that I get this, let's combine these two sequences together. Now, which way do I want to see those? Notice I have a G here and I have a J here, right? GJ and I have GJ. Well, let's put a constructive dilemma together. Let's combine these two things together. So I'm going to get if G then H and if J then K, right? And that is going to be lines 7 and 11 conjunction. And now that I've conjoined them, right, I have either G or J, which means line 13 is I must have either H or K, right? And that's line 12 and 3, constructive dilemma. And of course, there's my conclusion. I'm done, okay? So this is a sort of longer conditional proof, but notice you can do the conditional proof twice in a thing, right? You can also I'll do one last problem here because you can actually even embed a conditional proof within an argument sequence twice. So let's sort of show you what that looks like. If you have, if Larry goes to the party, then it's the case that if Mary goes, then Navi or Orion is going to go to the party. Line 2 here is, well, if Mary goes, then it's not the case that Navi is going. Conclusion, well, that means if Larry's going, right, then it's not the case that Mary's going or Orion's going, right? How would you know if this argument was valid? Well, we're going to have to do a proof. But you can see how would I know that I need to use a conditional proof? Well, the first dead giveaway is to see that there's a conditional in the conclusion, right? The fact that there's a conditional in the conclusion can lead us to say, well, if I did a conditional proof, it would work. How should I do a conditional proof? Well, what if I make this my assumption, right? Can I get to this as my consequent, right? That's the question. So line 3 here, if you really, obviously you're very stuck, you're not sure what to do, let's assume L then, okay? So that's going to be L. That is assumption for the conditional proof. Line 4 is if I have L, then I can unlock this ugly sequence. Now remember, write it off to the side over here. So that's going to be if M, then N or L. Oh, I'm sorry. And that's line 1 and 3 modus ponens. Right? Okay, now that I have this, what can I do? You can see here, ultimately, what I need to do, maybe, you can see, because what I need is if I have M, then I have O. That's kind of what I need, it looks like. I'm not sure where to go from here. So let's do another conditional proof. Let's assume M. So that's going to be A, C, P, right? And notice that this one is now going to be written off to this side, right? So that's going to be another conditional proof. So if I have M, now notice I can use these rules in order to do my conditional proof because it's embedded within another one, but ultimately it's not going to work if they already get discharged. Once something is discharged, it's done, but I haven't discharged anything, so I can still use these lines within the proof sequence. So if I have M, that means line 6 is I have N or O, right? So that would be line, line 5 and 4, modus ponens. Now that I have M, I have not N as well, right? So that's line 7 is going to be not N, and that's line 5 and 2, modus ponens. If I don't have N, that means I must have O, right? So that's line 8 here is going to be O, and that's because of lines 6 and 7, disjunctive syllogism. Now let's go ahead and discharge this now. So that's going to be line M. Line 9 here is going to be, if you have M, then you have O, right? And because I'm actually moving back, I'm still just writing the line here within this other proof sequence, okay? So you can imagine the line just continues going down from here. So if I have M, then O, okay? And that would be, now I have to discharge, which means I write lines 5 through 8, conditional proof. Right, but now, so that means once I've discharged it, these are now off limits. I'm not allowed to use these, but I can still use these up here. Now, notice this says if I have M, then O, right? What can I use here? Well, wait a second. Remember the rule of implication, right? And just to remind you what the rule of implication looks like, take a look here, right? So you can see here, this is an old book I have, but notice the rule of implication says if P then Q, I can replace it with not P or Q, right? So let's do that right here. So line 10 here is going to be not M or O, right? And notice that was the consequent I was looking for. But for O, whoops, you have to write down the reasoning you used, which was line 9, implication. And now that I have the consequent of the conditional I need, let's discharge it. So line 11 here is going to be if L, then not M or O, right? Where this goes here and the L goes over here. So that is lines 3 through 10 conditional proof, right? But now that they're discharged, these are no longer valid elements within the proof that could be used again if we wanted to go further than that. Obviously, we don't need to go any further, right? So this is a conditional proof that actually gets embedded within another one. But when you embed this, but once something gets discharged, that's the rule. You can't use it anymore. So literally, this is an interesting argument because literally the premises and the conclusion are all valid, but there's no other argument we could use outside of the conditional proof to prove that, okay? So that's how you do these problems. It's not too difficult. What's key to remember? once discharged, you can't use any conditional proof lines. Okay, so once something is discharged, it's done, and that's the important thing to remember. So let's take a look in here. I apologize again, we're sort of doing this old school instead of using the computer, but the same rules apply, so it's not too big of a deal. Okay, take a look here at what your book's going to ask you to do. It's basically going to say here's some homework problems. Of course, this is the old edition, so the 11th edition, the homework problems are different, but you can just take a look on Apple. And you can see here that essentially tomorrow we'll be looking at the indirect proof, but today we're going to be doing these sorts of arguments, and you just have to use the conditional proof sequence to drive the conclusions. Let me do one last problem here, and then we'll end our video here because the technology is not too great, but also it's not difficult to use these conditional proofs once you get a handle on them, right? Again, the real trick here is, again, to always continue to practice and know the rules of replacement and the rules of implication. You can think of this, you're going to see that the conditional proof, and especially the indirect proof, which we'll also cover, that these are sort of your nuclear bomb. They're sort of the, when you want to go nuclear on a problem and you really don't know how to solve it, it's sort of your last resort is to begin to use these conditional proofs, right? And you can get a sense here, of course, if you need to conclude something like this, right? What's the key off that maybe a conditional proof is to use? We'll notice we have a conditional statement. Well, for a conditional statement, that means this is an antecedent, right? And this is a consequent, which means that, well, maybe I should just assume N and see if I could get this stuff together. So let's do line 3. In fact, if you can, do this problem on your own, right? Do this problem, pause the video, and see if you can get how to do this, okay, using a conditional proof. So line 3 here is, right, let's assume N. So let's write N here, and then we'll write, this is an ACP, right? Sorry, my notes here make it a little bit difficult, right? So line 4 is if I have N, then I have O. So that's line 1 and 3, modus ponens, right? Line 5 is, well, if I have N, I also have P, right? So I can unlock the P. So that means that using modus ponens, so that's lines 2 and 3 modus ponens, right? And of course, now I can combine them together because remember, my goal is, right? My goal is to create this thing right here, right? Okay. I don't know if that highlighting makes it harder to see or not. Okay, so that means line 6 is to combine these, O and P, right? And that's lines 4 and 5, conjunction, right? And now that I've combined these, I want to discharge it, right, to get the antecedent and the consequent lined up in a conditional O and P, okay? And then my parentheses. And that's lines 3 through 6, conditional proof. And now that I've discharged it, you can see this is my conclusion. And the conclusion, since it was the one I was looking for, right, is valid. So this is the proof. And it seems sort of odd that you can make assumptions, but that's why you can make an assumption to see if your assumption, if it was true, if it would result in something, in that full sequence is valid, right? But you still don't know if you have N or not, okay? But the sequence here, or the conclusion where you were looking for, was not N. Otherwise, it would be impossible, or you'd have to use an indirect proof, okay? So this is what a conditional proof looks like. And again, I apologize for sort of the poor quality of this video because I'm trying to record these without I basically lost my stylus for my tablet, and I've had to order another one. It won't be here for another week. So the next couple videos may be by paper, but hopefully you can see how to do these problems as well. Okay, in our next video, we're going to look at the indirect proof, and we'll see that the indirect proof is sort of the last man standing argument. This truly is your sort of nuclear weapon. But more than that, it allows you to very easily, in a very able sense, build proofs when you have no other way to go. So next time we'll be looking at indirect proofs. Thanks a lot for listening. We'll see you guys online. Bye.